Welcome to Chapter 4, Electron Arrangement. When you're writing the notes for this lesson, you'll find that the ones that you need to fill in your blanks are going to be written in red. So you might need to pause it to be able to write that down. So let's get started with the basics. Energy that arises from the motion of the electrons is going to be said to be quantized. Okay, that means only a certain value of that energy exists. It's not random. That energy level or state involves either the absorption or the emission of that definite amount of energy. And we refer to that definite amount of energy as a quantum or a photon. So you might want to put a star by that. The energy can either be in the lowest energy state, which is called the ground state, or the highest energy state, which is called the excited state. When we have this excited state or ground state, it's going to either involve, like we said in the last slide, either absorbing energy or releasing energy. If it's absorbing energy, it's going to jump up from the higher energy levels, from 1 up to the higher energy level. Okay? Depending on how much it absorbs, it can stop along the way at the first one, or it can go all the way to the second one. But we know what goes up must come down. So in that case, then it releases the energy, and it can either fall back down to the energy level 2, or it can release enough to fall all the way back down to level 1. And when that does, the energy is released as a photon. And again, remember, it is in a specific amount of energy. All right. So we said this just now, either it's absorbed or released between the two states. When this happens, it's in the form of photons. You have got to know photons, put a star by it, okay, of electromagnetic energy, also known as light. We can determine the amount of energy using two equations, the speed of light and Planck's equation. So let's dive right into that. So before we actually use the equations, we need to define some of the variables that are going to show up. The first one is wavelength. Wavelength is the length of one complete wave. This little funny symbol right here is called lambda. It is a Greek letter, and we use it to signify wavelength. Frequency is the number of waves that pass a point during a certain time period. And amplitude is distance to the origin. We measure frequency, okay, in hertz, and something called hertz, okay? It's 1 per second, okay, 1 per second. And it's the number of waves that pass during a certain period of time. So kind of think of a pier. We've got a pier, and the waves are coming, and the frequency is how often are those waves hitting that pier. So that's a way to think of that. Now you see why I don't teach art. Okay, so here's what a wavelength looks like. Remember, we said it was a wavelength was from one point to the next point on the same wave. You can actually measure it anywhere on that wave. You just have to be in the same point on each wave. So I can measure it from the bottom if I wanted to as well. The peak, of course, is the top of the wave. The trough is the bottom. And then we said the amplitude is from the origin, which would be right here, until either the peak or the trough. Okay? And of course, frequency would be how often did those waves hit. Okay, if I've got a big wavelength, it's going to hit not very often, but if I have a small wavelength like this, the frequency is going to be higher. Okay, so that brings us to the speed of light equation. Before I show you the speed of light equation, I want to make sure that you understand this. Okay, and that is frequency and wavelength are inversely proportional. Okay, that is important, inversely proportional. That means if one goes up, the other one goes down. Okay, one goes up, the other one goes down. And that is because of this. Here is the actual equation. The speed of light is equal to wavelength times frequency. So anytime the product is equal to a constant, it's going to be inversely proportional, because you can see that if it's always equal to the speed of light, because it's for all forms, okay, of EM radiation, it says that right here. I would put a star by that. You will see it again probably somewhere and very important, okay? And so since it's the same for all forms, if I was to increase wavelength, I would have to decrease frequency in order for it to still equal the speed of light. And there is our lambda again, that funny looking upside down Y. And wavelength for electromagnetic radiation is typically going to be measured in nanometers. Okay, and then of course frequency was 1/2. So if I show you an equation, you know we're going to work a problem. This one says find the frequency of a photon with the wavelength of 434 nanometers. So that's going to be our lambda. So we're going to use this equation. Okay, we already know the speed of light because we gave it to us. It's a constant. It's the same for every form of electromagnetic radiation, which is 3 × 10⁸ meters per second. So the first problem I see, though, is that my speed of light is in meters and my wavelength's in nanometers. So I can either change my speed of light to be nanometers per second, or I can change my nanometers to be meters, which is what I prefer, so that's what I usually do. Okay, so I've got 434 nanometers. I'm going to need to get rid of nanometers and get to meters. So my prefix nano means 9 nanometers are equal to 1 meter. I always remember it by they both start with N, 9 and nano. So it takes 1 × 10⁹ nanometers to equal 1 meter, and that will give me 4.34 × 10⁻⁷ meters. So now I can use my speed of light equation. I'm going to rearrange to solve for frequency, so it'd be c over lambda. Okay? When you're using the speed of light equation, you will never put c on the bottom. Kind of like don't put baby in the corner, don't put c on the bottom. C is always on the top. Okay? If you don't know what movie I'm referring to, ask me in class. Okay? So now let's plug it in. 3.00 × 10⁸ meters per second divided by 4.34 × 10⁻⁷ meters. So now meters cancels out, and I need 3 significant figures. Remember, speed of light is a constant. We do not use constants to signify our how many sig figs we need. So we're going to use our nanometers. So 6.91 × positive 14. And that's going to be hertz. If you look at what's left over here, it's 1/2, which of course is hertz. So that is the answer to that. Okay? That brings us to Planck's equation. And Planck's equation states something different. It states that the energy of a photon is directly proportional to its frequency. And this word directly got left out of your notes. It just says proportional. So please add in directly. I would also put a star by that, because that could possibly show up somewhere very important as well. Okay? So, same kind of plug and go equation. We're just going to plug in our stuff and see what we get. Okay? So let's go do an example. This one wants to know, find the energy of a red photon with a frequency of 4.7 × positive 14. Okay? Remember, hertz is the same thing as 1/2. So I'm going to use E, H, V, or nu, whichever one you want to call. Remember, H is a constant for all forms of electromagnetic radiation, just like the speed of light is a constant. And it's 6.6262 × 10⁻34 joules times second. Okay? So we're literally just going to plug that in. 6.6262 × 10⁻34 joules times second. And then we're going to plug in our frequency, which was 4.57 × 10⁻14 hertz. And remember, it's 1/2, so they cancel out. We need 3 significant figures, because again, constants don't signify our sig figs. So that is going to be equal to 3.03 × 10⁻⁹ joules. And that would be my answer. Okay? Here's another example using the speed of light equation. So you're going to use this one right here. This time you're going to be solving for wavelength. So what I would do is I would pause the video real quick and see if you can't get the answer. and then move on to the next example. So pause here, work it out, and see if you get the answer. All right, so if you did that correctly, you should have either gotten 5.88 times 10 to the negative 7 meters, or 588 nanometers if you switched it back. If you left it in meters, because this did not signify that they wanted it in nanometers, you would have been okay. But if it tells you it wants it in nanometers or centimeters or whatever, and you don't put it in the right unit, then you will miss that on a problem. Okay? Here is another example, and this is going to basically marry the two equations we've done so far. Okay? This one wants to know the energy when it gives you wavelength. Okay? So you have two equations that you can use. You can use C is equal to the wavelength times frequency, and you can use E is equal to HV. Okay? Now, I'm going to show you something that you may or may not like, but I can simplify this by putting the two equations together. Okay, so you're welcome to use two separate equations. You're welcome to solve for frequency and then plug that in to solve for wavelength, or you can shortcut that by looking at this equation and saying frequency is equal to C over wavelength. Okay, if I rearrange that, and then I can substitute that in, so that my equation is now all in one is HC over wavelength. Okay? If you don't like that, then ignore it and use them separately. Okay? It's your choice. In AP Chem, we use that equation already put together. It makes our life easier. Okay? Again, no matter which equation we use, we cannot keep our wavelength in nanometers. So we're going to have to take that out because the speed of light is in meters. And from the last example, I gave you that. It's 1 times 10 to the 9th nanometers is 1 meter. So that's going to be 6.25 times 10 to the negative 7 meters. Okay? I'm going to use this equation. If you don't like it, you can do it separately and you should still get the same answer. So I'm going to say energy is equal to 6.6262 times 10 to the negative 34 joules times second. That's my H value. Plug in the speed of light, not negative, and divide by 6.25 times 10 to the negative 7 meters. Cancel out, cancel, cancel. So I'm going to have a unit of joules, so that's good. Everything canceled. So I'm going to plug that into my calculator. Here we go. Times the speed of light. And then divided by the wavelength. And I get 3.18 times 10 to the negative 19. Okay? Like I said, if you don't like that equation, you could have solved for frequency because you have a wavelength and then plugged it in and solved for energy. Okay? All right, so let's go on to now the electromagnetic spectrum, which you need for your homework. And looky there, we got the right answer. All right, so that brings us to the electromagnetic spectrum. Okay? All photons in the electromagnetic spectrum have the same nature. Okay, so they behave the same, but they have different energies and wavelengths. Okay? Different energies and wavelengths. Okay? So make sure you keep that. They behave the same, but they have different energies and wavelengths. However, they all have the same speed of light, which are all equal to 3.8 times 10 to the meter second, and then they all obey Planck's constant. Okay? These different energies cause the photons to interact with matter differently. Okay? Some are higher energy. The human eye can only see the visible region, which is between 400 nanometers and 700 nanometers. Okay? And when you were a little kid, coloring, and you wanted to know the colors of the rainbow, which is basically the visible region, not basically, it is the visible region, we did something called Roy G. Biv for the colors of the rainbow. Do y'all remember that? Red, orange, yellow, green, blue, indigo, violet. That's the colors of the rainbow. Okay? Red's at the top, indigo is down at the bottom, so it goes that way. Roy G. Biv. Okay? So here is our electromagnetic spectrum. Okay? Now, this is showing you the opposite of Roy G. Biv, because this particular spectrum is based on the energy and order of higher to lower is what it is. So over here is low energy, and you should label this on yours. Low energy, okay, high wavelength, we're going to use our lambda sign, and low frequency, okay? On this side, we have high energy, okay, low wavelength, and high frequency. Okay? Remember, that makes sense because energy and wavelength and frequency are inversely proportional. Okay? So red is going to be the lowest energy, and violet is your higher energy of the visible. Okay? So when you're looking at this, you just got to ask yourself which is lower, which is higher. Okay? Kind of makes sense, okay? Because right before the low energy red is infrared and then microwaves. Of course, we have microwaves in our homes. Okay? Violet is the highest of the visible that we can see, and it's right before ultraviolet rays, which of course what gives us sunburns, and then comes X-rays, and these are gamma rays. Gamma rays are your highest energy. They are also the most detrimental to human tissue. Okay, that's where we get like radiation poisoning and stuff from like the nuclear plants that, you know, back when the tsunami happened in Japan and they had the meltdown. That was gamma rays that was causing people to have radiation sickness, and or, you know, if you get enough of it, can cause you to die. Okay, so you will probably need to pull this spectrum up to do your homework when it's asking you the questions about which one is higher energy, which one's lower frequency. And so you just got to look at this and say, okay, if I'm low energy, I'm high wavelength, and I'm low frequency. Okay? All right. And I believe that is where we're going to stop today.